Okay, so today we're going to be taking a look at implicit differentiation. First of all, what's the difference between implicit and explicit? Well, if you're looking at equations or functions, an explicit function has your variable y or f of x on one side all by itself, where an implicit has x's and y's mixed together on the same side. So here we have an implicit equation. If you did go ahead and solve it for y, then you would get what we have over here on the top. Or here we have an implicit equation for a circle centered at the origin radius of 10. If you did solve it for y, well, then you would get this right here. So some implicit equations can relatively easily be solved for their explicit forms. Some cannot be. So let's look at this problem here. Find the slope of a tangent line to our circle, x squared plus y squared equals 25, when x is 3. You'll notice over here I have this as being the point. You might be wondering, well, how did I figure out the y value? Well, if x is 3, plug it in, get 3 squared, which is 9, plus 25, or plus y squared is 25. So we get y squared to be 16. You take the square root of 16, you get plus or minus 4. So that's where that comes from. So if you go ahead and solve this equation for y, you would get the explicit form right here. Remember, your square root's really the 1/2 power. So if we're looking for the slope of a tangent line, you know that that's derivative. So we put the exponent of 1/2 in front. Take this, decrease our exponent by 1, 1/2 minus 1 is this. Chain rule! Derivative of the inside, negative 2x. Now, in this case, you'll notice your negative 2 cancels out your 1/2, still with a plus or minus. You might be wondering, well, what happened to that negative? Well, a negative onto your positive is the negative on the bottom, but a negative onto your negative is really the positive that's on the top. Now, we're looking for our slope of our tangent line, our derivative at this point here. So x is 3. Plug in 3 for x. And the bottom, we get 25 minus 9, which is 16, square root of that. So we get 3/4. So it's plus or minus. Now, we could also do this one implicitly. So we're going to just do the power rule. Exponent in front, 2 in front, decrease it by 1. But then we have to do chain rule. We have to do the derivative of the inside, which is x, with respect to x in this case. So that's why we get a dx over dx. Here we take our exponent of 2, put it in front, but then we have to do chain rule, derivative of the inside, derivative of y with respect to x. Well, maybe under the derivative of that 25, you know, is 0. You might be wondering, well, why didn't we do the chain rule over here? Well, in a way we did. When you're doing the derivative of the inside, you do the derivative of the very inside here, you'd have a dx over a dx. Well, that's just 1, so it doesn't change it. So same idea here, our dx over dx is special form 1, not going to change it. Well, then all you have to do is try to get dy over dx by itself. So you can subtract the 2x from both sides, divide both sides by a negative 2y. Now, if you wanted to change your dy over dx to a y prime, you could, because dy over dx and y prime are identical in meaning. When you divide both sides by the 2y, you get this here because the 2's drop. So then you can plug in your point. Once again, your point was 3 comma plus or minus 4. So 3 and plus or minus 4 because y is on the bottom. So the negative over the positive is a negative, where the negative over the negative is a positive. So it's still plus or minus 3/4. So two different ways to be able to go ahead and figure out your slope of your tangent line, which is your derivative. By the way, as a side note here, it's not going to fit nicely. Can I move this up just a touch? Okay, so if we look here, you notice this is our derivative. However, if we take what y is right here and plug it in right here, that really, when we substitute that in, gives us, where'd my cursor disappear to? Gives us what we have right here. So that's another way you could kind of look at it, is it's really the same thing, just written differently. So basically with differentiation, you differentiate both sides with respect to x. Then you want to try to get all your dy over dx's on one side of the equation. Anything that doesn't have a dy over dx hanging out with it, you get to the other side. And then you can factor out your dy over dx and then get dy over dx totally by itself. So let's do our derivative here. Exponent in front, decrease it by 1. Then we have to do the chain rule. The derivative of the inside, which is y, derivative of y with respect to x. So that's a dy over dx. Here we have our x squared. So we put our exponent in front, decrease it by 1. Derivative of the very inside, derivative of y with respect to x. Minus, well, derivative of y, you know, is just 1, so it's just negative 5. But chain rule, derivative of the inside, derivative of y with respect to x. Minus, put your exponent in front, decrease it by 1, we get this. Then chain rule, derivative of that inside of x with respect to x. Derivative of the right-hand side, 0. Well, dx over dx we know is 1. So that doesn't change it a whole lot. But we want to try to get everything that doesn't have a dy over dx on one side. So we're going to take this to the other side because all these have that dy over dx. So we're going to leave that on the left-hand side. Now, if you look in the left-hand side, they all have a common factor of a dy over dx. So we're going to pull that out. Then you can look at what's left. A 3y squared, a 2y, a minus 5, still equal to that 2x. We're looking for dy over dx, so we got to just get that on one side by itself. So we got to undo multiplying by the parentheses. So we just divide both sides by the parentheses. So that's our derivative via implicit differentiation, which I'm not sure how you would go about doing explicit differentiation, because I don't think you'd be able to get y on one side by itself here. So consider this problem here. Now, we could do implicit differentiation. We could do explicit. But if it's explicit, you'd have to solve it for y. At this point, I'd be surprised if you knew how to solve it for y. But if you did get y on one side all by itself, you would get this big, ugly fraction with not a all of big fraction, but we have this expression here and then this fraction here. Both of them have a square root inside of a cube root, and in this case, it's a square root inside of a cube root in the bottom of a fraction. Don't really think it would be fun to take the derivative of this. Could it be done? Yes. So if we tried implicit instead, we put the exponent in front, decrease it by 1. Chain rule, derivative of the inside, derivative of that x with respect to x, well, there'd be a dx over dx here, which is really 1. Then here we come, we put the 3 down in front, decrease it by 1. Then chain rule, derivative of the inside of derivative of y with respect to x, so dy over dx, or y prime, same thing. Right-hand side, we'd have to do our derivative there, but notice, product rule! Woohoo! So, derivative of the first, derivative of 3x is 3, times the second, plus the first, which is the 3x, times the derivative of the second. Well, derivative of y with respect to x is y prime. Oh. So now all we have to do is try to get the y primes on one side, the things that don't have y prime on the other side. Does it really make a difference which side you take stuff to? Nope. So if you take your 3y and subtract it to both sides, you get this. Now we could take our 3y squared y prime and subtract it from both sides. So we would have this here. So this 3y, y prime just got brought down. Remember, we subtracted that over. So now we could go ahead and simplify this. Probably could have done it earlier, but get rid of all the 3's by dividing everything by 3's. Now I think on the right-hand side, I'm going to factor out a y prime. So do nothing over there on the left. The right-hand side, factor out my y prime. Huh. Now I just have y prime multiplied by something, so all I have to do is just divide by the parentheses, and hunky-dory, I'm done. That's my derivative. Now, looking at this, I don't really think it looks that bad. I do think that this whole process here was probably a little bit easier than trying to do your derivative of this whole thing right here. We eventually would have got the same answer, but man, it would have been a royal pain in the butt to do. So we want to find our IROC. Remember, IROC and derivative are the exact same thing, instantaneous rate of change at this point. Well, we got to find our derivative, and then all we have to do is plug in our point for x and y. Huh. Left-hand side, it's just a sine. Derivative of sine, you know, is cosine, so we don't do anything there. But chain rule, you have to do the derivative of the inside. Well, derivative of x with respect to x is 1 plus 2. Then you got to do the derivative of y with respect to x, y prime, or dy over dx. Right-hand side, well, we'd have to do our derivative here, but hey, chain rule is being applied with a product rule here. Oh, do we have a chain rule? Yes, we have chain rule. Sorry about that. So, derivative of the first, really be the chain rule, the dx over dx, so dx over dx would really be a 1, doesn't change it, times the second, plus the first. Derivative of the second, derivative of cosine, you know, is negative sine. Then you'd have to do times the derivative of the inside, derivative of y with respect to x, y prime. So all we have to do now is try to solve it for y prime. But notice y prime on the left-hand side is inside some brackets. So all I'm going to do is take what I have in front here, this, distribute it through to the 1 and to the 2y prime. So that under the 1 is this here. That on my 2y prime is right here. Right-hand side, I might just bring my negative out in front over there. So now I got a y prime on the right, a y prime on the left. All I have to do is get the y primes on one side, the non-y prime terms on the other side. Doesn't really make a difference. So I'm going to take my non-y primes, like this one right here, move it to the left side by subtracting it. This one right here has a y prime. I'm going to move it to the other side by subtracting it. So I will get this right here. Now notice in this particular case I have a negative, and a negative. 3 out of my 4 terms are negatives. So maybe for simplicity I'm going to just multiply everything by -1 and we would get this. Now, if instead of bringing all my y primes to the right side, if I took my y primes to the left side and what was on the left side I took to the right side, I would have got straight down to this answer here and I wouldn't have had all those negatives. But if you end up getting a lot of negatives, that's what you can do. So now you'll notice on the right we have a y prime as a common factor. We can pull that out. Didn't do anything to the left side. On the right side, we have y prime times something. To get y prime by itself, we just have to divide by this big set of parentheses here, and we get this. So now all we have to do is plug in our x being 0 in both spots, our y being 0 here and here and here. So you'd have cosine of 0, which is 1 times 2. Then you'd have 0 here plus 0 here. You'd have cosine of 0, which is 1. So you'd have 2 minus 1 on top. Then on the bottom, you plug in 0 here, plug in 0 here. You'd have 0 times 0, which is 0. Over here, you'd plug in 0, you'd plug in 0. You'd have cosine of 0, which is 1, times 2 is 2. So your slope is 1/2. Okay, so We'll do our second derivative implicitly here in just a bit.